Rayleigh-Ritz, Galerkin. These names, alone and in combinations, refer to distinct but related computational techniques. What are these techniques, and who did what? This webinar summarizes my journey through an investigation of these techniques, made concrete by implementations in Maple. And throughout this journey, I never ceased hearing the syncopated rhythm of the song, Puttin on the Ritz. The song. Well, this is the set of lyrics I got from the internet. They have been changed over the years since Irving Berlin first formulated them in 1927. And if you really want to treat yourself, look up on the internet this version from 1946 comes from the movie Blue Skies, where Fred Astaire both sang and danced to this song. It is an amazing 4 minutes of entertainment. Our roadmap through this material. These are the names. Rayleigh-Ritz. You'll find Rayleigh-Ritz in the literature, Galerkin, and Ritz-Galerkin. What are the techniques? Rayleigh quotient, approximate eigenvalues of a Hermitian matrix. What did Ritz do? Direct method in the calculus variations, and then an approximate solution of self-adjoint boundary value problems. Rayleigh-Ritz put the two techniques together, eigenvalues and solving self-adjoint boundary value problems. So you get approximate solutions of the Sturm-Liouville eigenvalue problem. Galerkin. He extended what Ritz did to more general problems, and you can even use Galerkin's technique to solve the eigenvalue problem, and so perhaps you would see in the literature Ritz-Galerkin as well as Galerkin. These are the references that I used. Applied Linear Algebra, 3rd edition, by Noble and Daniel. Clearly that was for the Rayleigh quotient. Boundary and Eigenvalue Problems in Mathematical Physics, Hans Sagan. Look at the date, 1961. I used this as a senior in college, 1962 going into 1963. Not a well-written book. I thought it was a good book, and as I pored over it in his Chapter VII on this material, I was not happy. He references this book, Approximate Methods of Higher Analysis, Kantorovich and Krylov, and he gives a date 1958. I went looking on the internet and got myself a copy. It's a 1964 date translation. So what's his 58? What's his 64? So I went hunting on the internet trying to get that date straightened out, and I ran across this recent note. Came from the American Mathematics Monthly in March of 2016, very recent. So here is a comment. Author claims 3 errors. It's not really 3 errors. It's extensions that these folks were not able to make because they were using pencil and paper. And he makes a very strong case for the use of tools like Maple, other computer algebra systems. But here's the date. First published in 1936 and first translated into English in 58. And subsequent translations, I got that 64 translation. Okay, so we clarified something, and also, amazingly, we have here an author who's promoting the use of technology, and he's pointing out that this phrase from medical science using handiwork. But these fellows who did this work back in the day when computers were not available, they struggled. So let's take a look at this Rayleigh quotient to begin. What is the Rayleigh quotient? Well, the definition you find is A is a Hermitian matrix. This is the quadratic or bilinear form. This is the norm squared. And if you're going to look at this formulation, you want to make sure x is never the zero vector. If you notice that with a simple scaling, the quadratic form becomes the Rayleigh quotient as long as you're looking over a whole space of vectors. And so this is an alternate formulation, much easier to work with computationally, just the quadratic form subject to the constraint that x is normal, unit vector. It avoids this constraint, which is much harder to impose computationally. Then Rayleigh's principle. Hermitian matrix, P by P dimension. Let its eigenvalues, which are necessarily real, be lined up from smallest to largest. Let the corresponding eigenvectors be orthonormalized, which you can always do. Line them up in the corresponding order. Now, consider the leftmost k eigenvectors, where k could be any number from 1 to p. Call that set, the span of that set, L left k, and the perp is the orthogonal complement. If you take the rightmost k vectors and the span, we'll call that Rk, and its orthogonal complement is Rk perp. And here's the principle. If you minimize the Rayleigh quotient over the leftmost first k vectors, you will get the eigenvalue of the next eigenvector, k plus 1. If you maximize over the rightmost set of eigenvectors, you will get the next lower eigenvalue. And to implement that, minimize and maximize, subject to the constraint of unit vector and orthogonality constraints, simple dot products. Okay, before doing any computations, we've got to find out why this thing works. So let's see if we can get some insight to see what's going on. So let's take a look at some pictures. Consider a quadratic form, reduce it to a sum of squares, and it's still subject to the constraint c equals 1. The norm is 1. Here are two examples, 2 dimensions, 3 dimensions, quadratic form that's been diagonalized, quadratic form that's been diagonalized. Here in 2D, this is a graph of the unit circle in red. This is a level curve of this quadratic expression. When the value of the quadratic form is such that its level curve is tangent to the constraint, you will have an extreme value. Okay, so 2. And you're going to pick out this 2 when it's tangent again at the top and bottom. That's here and here. That will be just about 3. You're picking out this value. The eigenvectors are the unit vectors along the coordinate axes, because this has been diagonalized. And here you have a picture in 3 dimensions. The green ellipsoid surrounds the unit sphere, because I have the value of this quadratic form at 4. As I diminish it, you'll see you get a point of tangency when the quadratic form is about 3. That picks out this value. Then again at 2, right there where it just touches on the side, that's 2. And then when it just touches inside the unit sphere, that's 1. So again, the unit eigenvectors would be the basis vectors along the coordinate axes. And so that gives you some idea why this Rayleigh principle works. Okay, we have to do an example of this Rayleigh's principle. So what maple constructs will help us here? I'll use the student linear algebra package. It's a little bit simpler to work in. I need variables, x, y, z, w, and u, and a vector x whose components are the letters x, y, z, w, and u. And then I'm going to alias the student multivariate calculus Lagrange multipliers command to the simpler LM, Lagrange multiplier. I want to work with a symmetric matrix whose eigenvalues I know. So here is a symmetric matrix. Look at this number, look at that number, etc., etc. And here are its eigenvalues. Now you might wonder, how did I manage to do this? Well, I ran across a paper that had an algorithm for constructing a symmetric matrix with given eigenvalues. So I played around. This was the matrix that I ended up with. These are the corresponding orthonormal eigenvectors. So they're in a list. So v number 1 will be this vector, and v2 will be this vector, and so forth. This is the bilinear form that A generates. X dot AX, a little bit of simplification. You can see here's some squares, y squared, x squared, and some cross terms. Now I want to do an extremization here on the Rayleigh quotient. So I'm going to use Lagrange multiplier technique in Maple. F is the Rayleigh quotient. This is the normalization constraint, norm x minus 1. This particular command wants the expression it does not want equal 0. The variables, we have x, y, z, w, u, and this output equals detailed returns every solution in the form x, y, z, w, u values, the corresponding Lagrange multiplier, and then the function value at that extrema. So I'm simply hunting through that collection of solutions, and for each such solution, picking out the function value that corresponds. They are going to be the eigenvalues 2 through 6, and just keep in mind that figure 1, why that's going to happen. Now let's do this minimization and maximization approach. Let's minimize over left collections of eigenvalues and eigenvectors. Now, in a sense, we know the solution before we calculate the solution, because we have to know these eigenvectors. But let's just check this out. Does this stuff work? Okay, so Lagrange multiplier, bilinear form, unit vector, orthogonality condition. So I'm looking in L1 perp. So I get a bunch of solutions back, and I hunt through there for the one that has minimum function value. And I print that out here. That minimum function value, minimum extreme value, is 3. This is the second eigenvector, and this is the solution that corresponds to this eigenvalue showing up, and they only differ by a minus sign. So it worked. Okay, so L1 uses the first eigenvector, so I get the eigenvalue to the right of that. Remember, it's 2, 3, 4, 5, 6, so I get the 3. And then it just keeps going. It works. Let's take 2. 1, 2. So here's 1, here's 2. I get back the next eigenvalue. Remember, it's 2, 3, 4. And the eigenvectors differ by a sign. I'm okay with that. Here's 3. 1, 2, 3. I get the next one to the right, which is 5. Eigenvectors are correct. Here's 4 of them going from left to right. I get the next one, which is the last one, 6. Now let's do maximize. So we're coming down from the right. So we take the rightmost one, which is 5, V5, do the orthogonality, and I pick out the max this time. I get 5 because it goes 6, 5. And here the eigenvectors don't differ in sign. It's just a question of which of the two solutions that correspond to that eigenvalue I grabbed. So here's 5, 4. And then I get the next eigenvalue, which goes 6, 5, 4. So I get the 4. Take the 3 of them. So 6, 5, 4. I should get lambda equals 3. If I take all 4 of them here, I'm going to get the last, or the smallest eigenvalue, which is lambda equals 2. But there's a min-max principle that goes a little bit further. I think the book by Noble and Daniel attribute this to Courant. At any rate, let's see what this is a more reasonable, more practical result. Hermitian matrix, P by P. Eigenvalues lined up, eigenvectors lined up, correspondingly orthonormal. We'll use the Rayleigh quotient in the form of just the quadratic form and unit vectors. Let CR be a subspace spanned by R arbitrary independent vectors. So CR is an arbitrary R-dimensional subspace, and CR perp is the orthogonal complement. If you maximize over CR, then take the smallest such maximum that you would find over a bunch of such R-dimensional subspaces, you would find lambda P minus R. So if R is 1, you would get lambda, in this case, 4. This computation, because you don't go over every possible subspace of dimension R, becomes an upper bound for this eigenvalue. And if you take the minimum over those subspaces, orthogonal complement of those subspaces, and then pick the largest of those numbers each number you get for one such subspace, you will find a lower bound for lambda R plus 1. So you're pushing up from the bottom. So the implementation is just the way we did it before, except that for these subspaces, I'm just going to pick random vectors to form the subspace. Now, of course, we want to implement this min-max principle. We want to see how this thing goes. Well, when I'm looking at a page full of subscripts P and R, and I'm wondering what's going on, I ended up sketching this out. Values of R will go from 0 up through 4. These lambda subscripts will be P minus 1, P minus 2, P minus 3, P minus... So I'm looking for lambda 4321, which are 5432. And this is what I will find when I do a min of the max. And when I do a max of the min, it's R plus 1, so I'm going to get 2, 3, 4, 5, 6. So here I'm getting upper bound, here I'm getting lower bound. Let me see if this works. So I begin with R equals 1. I want to do this calculation where I'm going to find an upper bound. I'm going to push up, find an upper bound for the lambda equals 5, and a lower bound for 3. So how did I do the calculation? Well, I did 20 subspaces. And how did I form the subspace? I just took a random vector. I kept the numbers small so I wouldn't give Maple too hard a time in its computations. There is the bilinear form. This is the constraint that keeps the vector's unit length. This is the orthogonality condition. So I'm looking in the subspace orthogonal to this collection. So it's CR perp. That's how I managed to do that implementation. Okay, so then I looked and I said, now wait a minute. I don't want to do this computation twice. There should be a way of getting the max and the min each time I do this. So that's what the extra coding here is. So I grab the solutions, get out the function values, I sort them from smallest to largest. So each time I do one of these subspaces and get function value, I want a list, smallest number, largest number. So I'm going to put the smallest number in one list and the largest number in another list. Then I'm going to take the min of the bigger number and the max, the smaller number, and this is what I print out. So I'm pushing down on 5 and I'm pushing up against 3. That's exactly what I'm supposed to have happened. Let R be 2. So the only thing that changes is that I now have 2 random vectors and 2 orthogonality conditions. Do the same kind of a construction. I'm pushing down on 4 and I'm pushing up from the bottom on 4 because that's the one's in the middle. When R is 3, I have 3 generating vectors. I have 3 orthogonality conditions. Same computation. I'm going to push down on 3 and up against 5. Notice I had to take a few more subspaces here to get reasonable accuracy. And again here, as I go to 4 vectors, R is 4. So now my subspace has dimension 4. So the orthogonal complement has dimension 1. So here are the constraints. And I'm pushing down on lambda equals 2. I'm pushing up against lambda equals 6. Well, that worked. So now we want to shift gears. And we want to look at 2 problems. Variational calculus and boundary value problems. So, variational calculus. What are the essential 2 problems in variational calculus we want to look at? Get extreme values of a functional of this type. You have the integrand as a function of x, y, and y prime. And you're looking for the y that makes the value of this functional extreme. So the y satisfy some endpoint conditions. companion problem is called the isoperimetric problem. You have the same functional endpoint conditions, but now y is subject to an additional constraint. This integral has a constant value, so isoperimetric. Where does this come from? Suppose this integral is giving you the area of a region, and this is the perimeter of the region. You have fixed perimeter. You want to maximize the area that that fixed perimeter can contain. Or this could be the energy of a hanging chain. And this could be the length of that hanging chain. And you want to minimize that energy to get the configuration that it's going to end up in. Those are two problems we want to look at. The indirect method is to have y satisfy the Euler-Lagrange equation. It's a necessary condition. Fy, so you take the partial of this integrand with respect to y, then you take it with respect to y prime, and you take the total derivative of that expression, the Euler-Lagrange equation. What do you do over here? You form a new functional. The original functional f, you introduce a Lagrange multiplier times this integrand, and you apply the Euler-Lagrange equation to the new functional. So it's f sub y minus d by dx of f sub y prime, where f is now this capital F defined here. Now there are direct methods. I'll point out two of them for solving these variational calculus problems. Euler's method. It uses finite differences. Discretize the x interval. Let the unknowns be the corresponding y values at those notes. Replace the integral by a sum, and in the integrand you have the unknowns yk appear, and use simple forward difference for the derivative. This gives you an expression in just the unknown yks. And then you minimize or extremize by differentiating with respect to yk and setting that equal to 0. So that's Euler's finite difference method. Here's what Ritz did. Ritz. Put on the Ritz. What did Ritz do? He said, think of a linear combination of basis functions, each of which have 0 endpoint conditions. They satisfy the endpoints, they vanish. And then tack on a function that satisfies the boundary conditions of the problem. Put that function in for y and differentiate it, then you get your y prime. When you do that integral, you're going to get an expression that contains just these coefficients, c1 through cn. Those are your unknowns. You want to minimize or extremize that expression. So take partial derivatives, like the ck, set that equal to 0. So that's what Ritz suggested. Now, how do we relate this variational calculus material we just looked at with boundary value problems? Okay, so we're going to consider second order. The coefficients have to satisfy some reasonable conditions. You can have boundary conditions, separated boundary conditions as general as this. Self-adjoint problem. So this is a formally self-adjoint differential equation. These boundary conditions give you a self-adjoint differential operator. You can look at the differential equation and pull out of it an operator. So you're looking at Ly equals something. It's reminiscent of an operator approach. Self-adjoint py prime prime. This can be tackled by either the Ritz or its extension by Galerkin, as we will see. Now let's go look over here. If you take that self-adjoint problem and have an eigenvalue version, see now this is the eigenvalue version. That's what Sturm-Liouville You got to pronounce it. I've looked it up on the internet and got a French pronunciation and an Englishman's pronunciation, but you got to somehow or other get that I in there. Liouville. Okay, so eigenvalue problem. You can formulate an operator that puts this into the shape Ly equals lambda y. It looks just like a matrix problem. Ax equals lambda x, Ly equals lambda y. And this can be tackled by Rayleigh-Ritz. Rayleigh for the eigenvalue approach, Ritz for that approximation approach. But one is Rayleigh looked at a matrix. Ritz looked at a variational problem, calculus variation problem. Somehow or other, it's got to be a bridge. And then since Galerkin extended what Ritz did, sometimes you see Ritz Galerkin. Okay, so now we've got to cross the bridge. Boundary value problems from optimization problems. Let's look at the self-adjoint non-eigenvalue problem. You have this functional which has this shape, this integrand, y prime squared, y squared, 2gy. Take the Euler-Lagrange equation of this functional. I'm going to do it. Differentiate with respect to y, so you pick out minus 2qy and minus 2g. Minus 2g. Then you will need the derivative with respect to y prime, so it's 2py prime differentiated entirely with respect to x. You have a negative 2, and you're going to have a negative 2. You get rid of those. This is p y prime prime. q y g. There's your self-adjoint boundary value problem. So if you have a self-adjoint boundary value problem, you can approximate the solution by approximating the extreme of this functional, vice versa. Okay? That's what Ritz used, because he looked at this differential equation, formulated it with this variational problem, and then used his direct method on this variational problem in order to solve that problem. So what about the Sturm-Liouville eigenvalue problem? Can we do this sort of the same thing with that problem? So there's your Sturm-Liouville eigenvalue problem. Get your lambda in there. Look at this variational problem. Extremize this functional subject to this constraint, this isoperimetric problem. How do you do that? You form a new functional. You take this integrand minus lambda times this integrand. Now, if you apply the Euler-Lagrange equation to that, you're going to first differentiate with respect to y. So you're going to get from here a minus 2qy, from here a minus 2 lambda wy. Then you have to differentiate with respect to y prime. So you're going to pick out 2p y prime d by dx of that. I put a minus here, put a minus here. So if you put those pieces together, you will have from here minus 2 py prime prime. From here, you will have minus 2 qy. So I factored out the minus 2 here, and you will get lambda wy. Get rid of that 2, and look at what you have. Py prime prime, q plus lambda wy. You have the Sturm-Liouville problem. So, you can attack the Sturm-Liouville problem as a isoperimetric problem in the calculus of variations. And if you can apply a Ritz technique to that, you might actually be able to solve this problem by solving that problem. And that's what Ritz Galerkin and Rayleigh focused on. Okay, let's apply Ritz to the self-adjoint boundary value problem, and we'll see where Galerkin figures in here. So this is just the self-adjoint problem. It's not an eigenvalue problem yet. Self-adjoint problem. Remember, you form this function. Now we're going to Ritz it. Putting on the Ritz. We're going to Ritz this guy. Form this linear combination of functions that vanish at the endpoints. Tack on something that satisfies the boundary conditions. Plug that capital phi into your functional where y and y prime has to be. You will get, after you integrate, a function of these coefficients. Differentiate with respect to each coefficient set equals 0, and you have a set of equations that you can solve for those coefficients. Now let's examine this further. Here is the functional after you've made this substitution suggested by Ritz. Now I've put a dot rather than a prime. Treat them both the same. And the reason why that is prime squared just doesn't look too good. And then there's an even bigger problem. Down here, when you want to take a derivative of something that's subscripted, Maple just does not put the prime above the k. It puts it to the right, or it'll push the k to the right. And that drives me crazy. So the dot at least sits on top of the letter. So just think of the dot as the prime. Okay, so according to this recipe, it's p y prime squared, so it's phi prime squared, y squared, y. Then you're going to differentiate with respect to the ck. So just imagine what happens there. Now this thing is got a sum of ck's in there. You're going to get 2 times phi dot times the derivative with respect to the coefficient. So that's going to pick out this basis function. Here, you again pick out the basis function. There's no derivative here, so there's no derivative here. And then here, you're going to differentiate with respect to the coefficient, and you're going to pick out the basis function. So look at this expression. This has a small phi k. This has a small phi k. This has a small phi k prime. It'd be nice if this were phi k also, and you could factor it out. So what is this? What's suggested here? Integration by parts. Let's integrate this term by parts. Take p phi prime as the u, which will get differentiated, and take little phi k prime as the term that will get integrated. So it'll go up to a phi k. So here's u v. Now these basis functions vanish at the endpoint, so this is gone. And you have minus, there's your v, and this is your du. So minus, 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 phi k, phi k, phi k. Put that together. Factor out the phi k. When you put this stuff together, what you are looking at is L phi, and that's where Galerkin steps in. He says, look, this is the residual you get when you apply the differential operator to your approximate phi. You want this integral to be 0. Well, this is an orthogonality condition. You would like this residual to be orthogonal to each of the basis functions. I mean, if the residual itself was 0, you made a lucky guess. You were great, right? But in general, it's not. And so Galerkin points out here that you don't have to come down through the chain of a variational problem. This will work with any differential equation. And so that's his generalization of what Ritz set about. And in general, people take these basis functions themselves as orthogonal. So you have the residual in function space orthogonal to as many orthogonal directions as you can, driving the residual towards the zero vector more and more. So there you have the essence of what Galerkin added to Ritz. So now we're ready to do an example. So the example I wanted to do was I just want to check out Galerkin method on any boundary value problem. This is not a self-adjoint problem. It is not an eigenvalue problem. Just a differential equation. Let's see if you can really get away from the restriction that Ritz would have faced to a self-adjoint problem. And I've taken these boundary conditions. Not even homogeneous. Well, this problem Maple can solve exactly. And there's the exact solution. Now I'm going to try Galerkin's technique. I need some basis functions. So I took these two. They happen to be orthogonal because when you integrate phi 1 against phi 2, you will get 0. If I tack on x, I'll meet these boundary conditions on 0, 1. So here's my Galerkin approximation. I plug that into the differential equation. I get a residual. I want this residual to be as close to 0 as I can possibly make it. How do you do it? You make it orthogonal to phi 1 and phi 2. So those are integrals. Maple can compute them. I have these two equations to set equal to 0. I can solve those equations for the two coefficients a and b. I put those into my Galerkin approximation. I have the approximate, and then I graph the exact solution and the approximate solution, and it's just amazing how close they come. Galerkin works for a boundary value problem. Now let's see what happens in an eigenvalue problem. So I'm going to take an eigenvalue problem and I'm going to get as close to an exact solution as I can possibly get, because then I'm going to do Galerkin and I will see how good a job it does. So differential equation py prime prime plus lambda y. Nothing fancy, but I just took p to be root of 1 plus x so I don't get a trivial solution. Homogeneous boundary conditions, y0 is 0, y3 is 0. If you would throw this into Maple desolve, you're going to get the 0 solution back because Maple can't do the eigenvalue problem. So the technique that I've done a recorded webinar on this, the technique that I have evolved that works the best for these kinds of cases is get the general solution when you can. Because if you can get the general solution exactly, then you can do what I'm doing here. So solve DE without the boundary conditions. General solution, two constants. Apply the boundary conditions. They will give you two homogeneous equations, because the conditions are homogeneous, two homogeneous equations in C1 and C2. And I put that in matrix form for the coefficient matrix. Now, these are homogeneous equations. If the determinant of this matrix is not 0, you're out of luck. You're going to get C1, C2, 0. So you got to have the determinant of this matrix be 0. So here's the determinant. You set it equal to 0, and you start solving for these lambdas that make this thing 0. So I use the Student Calculus 1 roots command because it will give me all of the solutions in a given range. I get 5 solutions, and I don't have to mess with fsolve and all the intricacies of getting fsolve to give you multiple solutions and repeated calculations and jumping all around the place. So there, roots command. Now I want to get the first eigenfunction. So I've got an approximate eigenvalue, and it's as accurate as I'm going to get with 10 digits. If I want it more accurate, I increase the digits, and I do this solve step again. So I treat this as an accurate number, but it's not exact. If you were to take that number and put it back into the differential equation right there and try to solve the differential equation saying, well, now I know lambda, so I ought to be able to get y. No, because it's not exact. Maple's going to still give you the zero solution. And if you come back over here and you put that lambda into this matrix, it's not going to be seen as a singular matrix because it's not exactly the right value of lambda. It's a little bit off. It's off by a little decimal. So here's the technique. Take one of the conditions, y of 0, for example. So you're looking at one of the equations, and you solve that for one of the unknowns in terms of the other. You put that into the general solution, and you'll notice you have a multiple of the eigenfunction, which is what you get anyway. And you can determine that constant by normalization. So here you square and integrate, and you get this equation to determine a constant multiple, and they're either plus or minus. So the eigenfunction is going to have one shape or the negative. And we put it all back into the solution. There is an expression for a normalized eigenfunction corresponding to that eigenvalue, and this is the graph. And for comparison, for corroboration, I will do the following. I will employ a technique in Maple that was programmed by a developer who does a lot of desolve work, or numeric desolve work. Apply desolve to the differential equation, the two boundary conditions, and throw in one more condition that you make up. So that the fact that lambda is not known is accounted for by one more equation. Get a numeric solution. So Maple comes back with a list of procedures, and if you evaluate those procedures any place, you will see a value for the eigenvalue. Now if you graph the corresponding solution, you'll notice that this doesn't go up to 0.8 the way our normalized eigenfunction did. And I phoned the developer. We've corresponded many times over the years, and I said, does Maple normalize this solution in any way, or does it try to normalize it? And he says, absolutely not. What you get is what you get. Okay, so we have a problem that we pretty much know the answer to. Let's see what happens if we do this Ritz-Galerkin approach. So we need some basis functions. So I have defined these 5 basis functions, and you notice they each have an x and an x minus 3, an x and an x minus 3. So they will vanish at the endpoints. Why did I pick these? Well, if you know something about the behavior of Sturm-Liouville eigenvalue problems, you know that each eigenfunction interlaces one more zero between the zeros of the previous one. So I picked functions that would have that property just to see if that gave me a better approximation, but they're not orthogonal. Okay, because this is the matrix of integrals phi I, phi j. This is not a diagonal matrix, so they're not orthogonal. I just want to see what would happen. So, differential equation, Galerkin's approach. I need some functions phi k, big phi k. So I take linear combinations of these basis functions. I don't need a phi 0 because I've got homogeneous boundary conditions. So let n be 1. This is the residual when n is 1. Multiply by little or a first basis function, you get this, which you want to be equal to 0. It's homogeneous in A1. Well, if you don't want A1 to be 0, then you need the coefficient of A1 to vanish. And so pick out that coefficient, solve for lambda, and that's an approximation to that first eigenvalue. Let's try this for two basis functions. So here is the residual when you use phi 2, which is a sum of the first two basis functions. You multiply by first basis function, you multiply by second basis function, you evaluate those integrals, you set them equal to 0. Again, these are homogeneous equations. So if you put it in matrix form, you have the same issue. Determinant has to be 0. So there's the determinant. Get the values of lambda. There are two of them. You notice that this is pushing down on that first eigenvalue, and this is pushing down on the second eigenvalue. Let's try 3. Residual, when you use the third approximating function, and then you have basis function, basis function, basis function. You have three equations. They're homogeneous, so you form a matrix of coefficients. The determinant has to be 0. There is the determinant. It's cubic, and you get three solutions. This is, again, first, second, third eigenvalues, and you're pushing down, you're approximating from above. So, seems to work. Now, at this point, I said, can I get an eigenfunction out of this? What's involved in getting an eigenvalue out of this? And the rationale here is the same as I explained earlier. If you use this approximate number, which is now really approximate, neither the differential equation can be solved with dsolve, nor is the matrix M going to be singular. So what can you do? So here's what I tried. I took phi 3, using phi 3, two of the equations only. So I solved for two of the coefficients in terms of the third. So A1 is a multiple of A3, A2 is a multiple of A3. Put that into phi 3. There is one constant yet to be determined, which is what you always get when you do an eigenvalue problem. The eigenfunctions are unique to within a multiplier. Normalize. So here's normalization. Okay, and after normalizing, this is what you get. I drew a graph, and you notice I shrunk the graph a little bit. The upper limit here on the graph is 0.8, so I think this is closer to the exact solution that we got. But a little bit, the normalization that dsolve does not apply has been applied here. Now, an alternate view of the computations we just did in this Ritz-Galerkin solution technique would be this. This is the residual. This is a basis vector. We want these integrals to be 0. There's your 0. And what do these integrals look like? These are the images of the residual. Let's break this integral here at the plus sign. Let's look at this term, and let's shift the derivative to the basis function by integrating by parts. That's going to bring out a minus sign here in front of this integral. Let's multiply through by that minus sign, so we have a plus in front of this integral, and we have minus lambda over here. Now, I'm going to define a vector and two matrices. The vector is the vector of unknowns, these coefficients. The matrices are these two sets of coefficients. Now, because of this minus sign, we have the generalized eigenvalue problem, AC minus lambda BC equals 0, or AC equals lambda BC. Now, in order to see where these terms come from, let's look at an example. Let's let n equals 2, so that the approximating function has two basis functions and two coefficients. And so this is what we're looking at. Now, there are two terms in here, and here are the two terms. There are two terms in here, here are the two terms. You have two integrals, or two equations to look at. Here you've integrated with basis function phi 1, and here basis function phi 2. Now let's split again at the plus signs and pull out the coefficient. Here I pull out a1. From this one I pull out a2. I'm looking at this term as a multiplier of a1 and this term as a multiplier of a2. Then the same thing here, multiplier of a1 and a multiplier of a2. Those are the terms that are called the alpha and the beta, a1, alpha 1, 1, a2, alpha 1, 2, and so forth. These equations can be put into matrix form this way. And that's where I get AC minus lambda BC equals 0. Now, bring that over to the other side, so it's AC equals lambda BC. Maple has a command that will solve this eigenvalue problem when you give it this matrix A and this matrix B. And that's what I do here. I do the computations of the matrix A, I do the computations of the matrix B, and I give the eigenvalues command the A and the B. And I do it for a variety of these approximating functions phi, not just phi 1 or phi 2. I do it for phi 1, 2, 3, 4, 5. Okay? Each time I do the calculation, I'm going to get eigenvalues, or generalized eigenvalues. If there is one basis vector, I'm going to get one eigenvalue. If there are two basis vectors of basis functions, I'm going to get two eigenvalues. 3, I get 3, 4, I get 4, 5, I get 5. These are essentially the exact eigenvalues. So in this tableau, if you go across the row, you are getting approximations from above that converge down to the actual eigenvalue. Same thing in this row. They converge down to the eigenvalue. Unfortunately, as you go further out, the approximation gets worse, so you need to take more terms. We've looked at the Sturm-Liouville eigenvalue problem essentially through the eyes of Galerkin. Now let's take a look at it through the eyes of Rayleigh-Ritz. So the Rayleigh-Ritz approach, you replace this eigenvalue problem with this variational problem, or you replace it with this problem subject to this constraint. So let's use this approach. You replace y with phi k. This big phi k, remember, is a linear combination of k basis functions. Put that into this integral, and you get a function of these coefficients. Put it into the constraint, you get a function of those same coefficients that has to equal 1. Then apply the Lagrange multiplier technique, and if you remember, look back what we did here, figure 1, as a motivation for why this is going to work. So let's implement that in Maple. Let's see where that takes us. So we'll take one term, one basis function, and one unknown coefficient. Our objective function is determined from here. That's called the objective function. The constraint function is here. So the Lagrange multiplier method applied to the objective function. This is the constraint. There's one unknown. And so I'm picking out from this list of functions, solutions that I get back, the value of the objective function at the solution. And so this is an approximation to the first eigenvalue, and it's an approximation from above. Now let n be 2. So now we use phi 2. All that changes here is that you have two unknowns. And so when you grab function values, values of the objective function, there will be two of them. And you have now approximations of the first and second eigenvalues. And you notice this one is now being pushed down from above. Now let's do it with 3 terms. So the only thing that changes here is that you have 3 unknowns, and so you will get back 3 eigenvalue approximations. And again, you're approximating from above. 4 gives you these 4 approximations. 5 gives you these 5 approximations. If you draw the graph of the 5th function, capital Phi, using the smallest value of lambda, you get this shape for the eigenfunction, and that 0.8 there leads me to suspect that this is very close to what we had earlier. We have the constraint that the eigenfunction has the magnitude or a norm 1. And if you take those numbers that we've just been computing and you put it into the same tableau, one function, 2 functions, 3, 4, 5 in the approximation. So you get more and more approximations to more and more eigenvalues. And this is the column of what we call exactly computed eigenvalues. And you see we're approximating from above each time, pushing down. And you'll notice that here the approximations get worse and worse because you got to take more and more terms, which you could do if you have a tool like Maple. You're not going to do this if you're working with pencil and paper. And so we've come to the end of our journey through these explorations at what Rayleigh and Ritz and Galerkin were talking about. Without Maple, I tell you, this would have been impossible, at least for me. With Maple, I was able to generate, at least to my mind, insights that were both pleasurable and resounded with that magnificent dancing and singing scene from Fred Astaire, Puttin on the Ritz.